Now that we've seen how data flow works, let's see how we can add a concurrent activity to the language. So we need to do this as a new language concept because the language we've seen up to now does not have this. So let's say that an activity is a sequence of executing instructions. So it's a sequential program. So let's add this to the language and we call it a thread. So each thread is sequential. It's a sequence of instructions. Each thread is independent of the others. That means it's exactly like concurrent activities, which are independent. There is no order defined between the different threads. No relative speeds. One might go faster, slower, anytime. It might slow down and then speed up. There's no speed defined between the threads. And the execution happens according to what we call interleaving semantics. What it means is that anytime there's only one thread executing, it executes for a few instructions, and then the system stops it, and then executes another thread for a few instructions, and stops it, and so on. So all the threads get their share of the processor's capacity through the system, which is stopping and starting them. So from each thread's point of view, it's as if it's executing, but only with part of the processor. So we say that the system is fair if each thread has a reasonable non-zero percentage of the capacity of the processor. And then we can program data flow. For example, two threads, they can communicate if they share a variable, like the example we saw. So let's see how to create threads in Oz. So creating a thread is simple. Any instruction can be executed in a thread. We in fact have a new instruction called thread end, and we can put any instruction inside. So here's an example. So we do thread browse x plus 1 and thread x equal 1. And both of the threads start. So this first thread starts first and the second thread starts after. But it does not mean that the browse will execute before the x equal 1. In fact, we don't know. This thread, first one, might start and immediately slow down a lot. And the second one might start and immediately run. We really don't know. So the relative speeds between the two threads can be anything. So this happens because the threads are independent. Independence means there's no relative speed because then they wouldn't be independent. So this browse x plus 1, if x is not yet bound, it will wait. And when x eventually gets bound to 1, this browse, the addition will execute and then the browse will execute. And if the x equal 1 is bound first, then the browse will also display 2, but it won't wait. So several executions are possible depending on the relative speeds of the threads, but they all eventually arrive at the same result. 2 is displayed. So here's a simple example with several threads. So I have 4 identifiers corresponding to 4 variables, and putting the in here means that everything that comes after is going to be executing and not defining identifiers. Everything that comes before the in is defining. So the declare in is like a local in. So here we have a thread doing an addition, another one, and then a browser which browses all 4 in a list. So it starts out by browsing 4 unbound variables. Notice the browser is also a data flow program. When a variable is bound, it will update the display. So let's continue now. So these two threads will be created and they immediately will wait. So x1 is 1 plus x0 will wait since x0 is unbound, and x3 is x1 plus x2 will wait since both x1 and x2 are bound. Okay, now let's do something. Let's bind a variable. Let's bind x0 to 4. So what will happen? Well, the first thread, this one which is in red here, now has both of its arguments for the addition, so it will execute the addition and it binds x1 to 1 plus 4, which is 5. So the browser updates and displays 4, 5, x2, x3. Okay, now this thread terminates, so let me just write it in gray. The second thread is still waiting. x1 is bound, but x2 is still unbound, so the second thread will still wait. So let's do another binding. Let's bind x2 to 7. This will cause the second thread to resume execution since the addition will have both of its arguments, and it will bind x3 is equal to 12 is 5 plus 7. Okay, and the browser will now be updated and display 4, 5, 7, and 12. So you see how the data flow execution goes. It passes information from one thread to the other, waiting when the information is not there, and continuing when the information becomes available. Let me just say a few words about the browser in this example. So the browser is in fact a data flow program. It executes with its own threads, and when it has an unbound variable to display, it creates a thread internally that waits until the variable is bound, and when the variable is bound, it updates the display. Notice that this does not work with cells. The browser is really targeting the data flow paradigm. It does not look at the content of cells, since they are not doing data flow.